This is the fifth lecture in strength of materials. In this lecture, we will see some of the most important concepts in the analysis of beams, which are known as shear force and bending moment. Shear force and bending moment diagrams for beams are very important concepts, and they have enormous applications in engineering, especially in civil engineering and aerospace engineering. What is shear force and what is bending moment? So let's take a simple example to elaborate on what these are and how to arrive at the diagrams. So I will take a very simple case of a cantilever beam. This cantilever beam is like this. Its length is L. There is a force applied P, and we take coordinate system which is like this: x and y. X along the length of the beam, y along the transverse direction of the beam. Now, because this is a two-dimensional problem, so we know that there will be three equations of static equilibrium, and there will be three unknown quantities for which we have to solve. So I isolate the beam like this. I apply the force P. The reaction will be R, and there will be a moment reaction which is called M. Now, before we go and see the analysis of beam to get the shear force and bending moment, we have to first see what is the sign convention we use for these quantities. The sign convention. The sign convention is like this. A beam is a long member having an area of cross section. This is the area of cross section of the beam. And the beam is having length along x-axis and the height along y-axis. The area of cross section, the outward normal to which points along positive direction of x, is known as positive cross section. And the area on which the outward normal means the normal which is coming out of the material, points towards the minus x direction, is called negative cross section. Now the convention is like this. If we take the beam again here, now this is a cross section, and because this is plus x direction, so this is the positive cross section. The shear force which is acting in positive y direction on the positive cross section, and this is the positive y force. So this force is acting in positive y direction on the positive cross section. This is conventionally called positive shear force. Now the same thing is followed here. The shear force which acts in negative direction on the negative plane is called positive shear force. Now, why is it important? It is important because of this reason. If I say that there is a plus 10 Newton of shear force acting on a beam on its plus x end. So for example, in this case, in this example, this P is acting in positive cross section because this is the end point which is in plus x direction, and this force acting plus y direction. So this is a positive shear force. So if I say that there is a plus 10, there is a 10 Newton force acting on A, let's say this point is called A, it should be immediately clear to people that the direction of force when seen in geometric sense, like this diagram, is this. Similarly, we can invert the direction of forces here and say that this is negative shear force. Similarly, this is negative shear force. This is a convention, which means that we can of course use the other way out also, but this makes life very easy for us to draw the diagrams. Same thing goes for the moments. I have this beam. The positive bending moment on the beam bends the positive cross section anti-clockwise, and it bends the negative cross section clockwise. So this is a set of positive bending moment. And of course the converse is true for negative bending moment. So the negative bending moment bends the positive cross section clockwise, this is clockwise bending, and it bends the negative cross section anti-clockwise. So this is negative bending moment. Now of course a lot of authors follow the other way out, which means that they say that whatever we have written as positive will be negative for them, and whatever we have written as negative will be positive for them. But that's immaterial because the directions are all arbitrary and we can always change the convention as we want. The problem again which we have a cantilever beam. There is a force acting here P, and the reactions are given like this. Let's assume that the reaction is R, the moment the force reaction is R, and the moment reaction is M. Let us assume that these are the reactions, and the length of the beam is L. Now you see P is a positive shear force because it is acting at the positive end, or it is at a positive cross section in plus y direction. This is y direction. And this is x direction. This is y direction. Now let's see. Let us write the equilibrium of this beam. So we have sigma f. Of course, I will not write x because now it is not required. Fy is equal to 0. That gives me the force P in plus direction and R also in plus direction. That gives me 0. Okay, so that gives R equal to minus P, which means the R should be acting like this. So R is like this. This is P. Similarly, I write sigma M is equal to 0. That gives me PL is anti-clockwise moment plus M also, which is acting, we have assumed to be anti-clockwise, so that is equal to 0. So that means M equal to minus PL, which means N acts like that. So that is equal to PL. So now we have the reactions for the beam. Now let's see what happens if we cut the beam at a particular section. Let's say I cut the beam here, some location X from the fixed end, and I take the left hand of the beam, the left cut section. So here I have one force which is acting like this P, and there is a moment acting like that M. Now you please see both this P and M are also positive shear force and positive bending moment. The reason being P is acting on negative cross section in negative y direction. So it's also a positive shear force conventionally. Similarly, this M is acting clockwise on a negative cross section. So this is also a positive bending moment. Now let's see what happens at this section. Now at this section, to have equilibrium, we must have some force acting like this and a moment acting like that. Correct? Because we have to have the equilibrium of this cut section of the beam also. This is called the SF and this is the BM. Okay. Now if we write the equilibrium of this beam, this section of the beam, sigma Fy is equal to 0, that gives me SF minus P equal to 0, which means SF equal to P. And if I write sigma M equal to 0, that will give me, this is X, I have a clockwise movement here M, so that is minus M, and anti-clockwise movement here BM, so plus BM, plus let's say I am taking the moment about this fixed end which is called O, so that will give me plus SF multiplied by X equal to 0. So I take out this PM, which is the unknown quantity here, is equal to M minus SF equal to PX, so that becomes the equation for BM, the bending moment. Now let's draw the diagram for shear force and bending moment. So this is the whole beam, this is O and this is point A, and let's see how is the shear force. So shear force is always equal to the applied force P, and see shear force is P, which means it is plus P, which means it is a positive shear force everywhere and it is independent of X. So the shear force acts like this. This is the shear force plus this is P, this is O, this is A, P. This is the shear force diagram, SFD. Similarly, if you draw the bending moment diagram, it becomes, I can just draw Y and X also so that it is clear what the axes are. This is Y and this is X. Now here bending moment is M minus Px. That is nothing but, what is value of M? The value of M is minus PL minus Px. Now you see, I have accidentally used minus PL here when the M was acting in anti-clockwise direction there. But in this equation I have corrected the direction, so this has to be taken as plus PL, because here it is already acting in clockwise direction. So in this case it becomes PL minus X. Now at X equal to 0, the bending moment is PL. This is PL. And at X equal to C, at X equal to 0, BM is equal to PL minus 0, that is equal to PL. It linearly decreases, and BM at X equal to L is 0, because PL minus X will be PL minus L, which is equal to 0. So at L it becomes 0, drops down linearly to 0. This is point A. So this is 0. So this is the bending moment diagram for the cantilever beam. So you see, it gives a lot of insight into how the bending moment and shear force diagrams work for a particular type of beam and particular type of configuration of the beam. This configuration of the beam is cantilever beam. So over here, the shear force and bending moment diagrams vary like this, which means that they look like this. The shear force for a cantilever beam is a constant if the force applied is P. The reason is it is a P force which is everywhere throughout the section. There is no change in P anywhere. So it is always the same force which is acting at every cross section of the beam. If we cut it here also, the same P will be occurring. But of course the bending moment is decreasing. This point will have a different bending moment, this point will have a different bending moment. At this point the bending moment is highest, which is equal to the reaction moment. Reaction moment is M. Now let's see. Now this is probably the simplest case. Now let's see what the bending moment and shear force diagrams for a simply supported beam look like. So I take a generic simply supported beam. I have a beam which is simply supported here. It has a pin support here, and so I take a simply supported beam having pin support at the left end and a roller support at the right end, and I take a force P acting at some location A from the pin support or from the left end, and the rest of the length is B. So the total length is A plus B, obviously. So this is the applied force P. Now I isolate the beam and I put the force P alone. This is B and this is A. Now obviously from previous class we know that the reactions will be proportional to the other side length, which means this reaction will be equal to, let's say this is called reaction B, that will be equal to PA upon A plus B, while this reaction A will be equal to PB upon A plus B. Now let's see how to draw the bending moment and shear force diagram for this beam. So let's say we cut the beam here, some location X away from the left hand end. So I have the isolated or the free body diagram for that end. I have one reaction RA that is equal to PB upon A plus B, and I assume that there is a shear force SF and bending moment BM acting here. Now you see, because I am assuming them to be these numbers, I am assuming them to be acting in positive directions. So I write the equation of equilibrium, sigma Fy is equal to 0. That makes SF is equal to, or sorry, SF plus RA equal to 0. So that means SF equal to minus RA, which is nothing but minus PB upon A plus B. I'm sorry. Now for simplicity, I assume A plus B equal to L. I was just for simplicity. So the shear force is equal to minus PB upon L. Now what is the BM? Sigma M, let's say about this point, which is called A, is equal to 0. So that gives me the BM which is acting there, BM, it's positive, plus SF into X is equal to 0. So the BM is equal to minus SF into X, that is nothing but PB upon LX, because this is already minus. Now at the point where the force is acting, there is something else which is happening. So this equation will not be valid if you go beyond this point. So only till A, only till X equal to A, these equations hold. So let's draw the shear force and bending moment diagram for this beam till point A. So how does they look like? The shear force is minus PB upon L, and it's a constant, which means that it is independent of the value of x until A. So this is the length and this is the point where force is acting. So this is minus. So it comes here, goes up like that. This is minus. And this is the y direction. This is x. This is the length of the beam. Point A, this is point B. This is point P, whatever. So this is the shear force diagram till x equal to A. So this is A. Now let's see what happens if we cut from here. Or if we take this section. We can take this section also and see what happens. Now we take this section. So that section is like this. And there is a force P. And there is this length which is A minus x, which is the remaining length, and this is B. Now this is RB. Now obviously this will not help us because the moment x becomes equal to 0, then this force will come and the equations will change. So what we need to do is that we have to cut the beam here and use that. So we cut the beam here and then we can take this section itself. We can take this portion. So I cut the beam there. I do not use this. I cut the beam there. This is P, this is A, and this is some x, and this is RA. So I assume this is the shear force and this is the bending moment acting there. I write the equation of equilibrium, sigma F is equal to 0 will lead me to SF plus RA minus P equal to 0. So that will mean SF equal to P minus RA, which is nothing but RB. Correct? Because RA plus RB equal to P. That is equal to PA upon L. Now this is also a constant. You see it is independent of x. So I draw this diagram here. Goes like that. This is positive. And this value is P. This value is P A upon L. And this is minus PB upon L because it is minus. Now, similarly, I write the equation of bending moment, sigma M. Now, at this section, I can write the moment about any point I want. Let's say I write about this point only. A is equal to 0. That leads me to the bending moment M, Bm, plus the shear force into x plus A minus PA is equal to 0. So that gives me Bm is equal to the shear force, which is PA upon L, minus, so that becomes PA. This is P multiplied by A. So PA minus SFX minus SFA. So that is nothing but, if you solve this equation, it will become SF is equal to PA upon L, and this is PA upon, this is PA minus, I'm sorry, this is PA upon L this will become PA minus SF into X minus SF into A, of course. So that will be PA minus A minus SF is PA upon L, so that is A square by L minus AX upon L minus A square by L. Now for x equal to 0, which is this point, this will be PA. I think I am doing something wrong, so I will just draw the diagram again. I'm sorry to disturb here. Please bear with me. Yeah. So I just draw the diagram again. and I write the equation of that equilibrium again. So I am solving this problem. I have this beam E, this is A, and this is B, and this is RA, that is equal to PB upon A plus B, and this is RB, that is equal to PA upon A plus B, and I have cut this section here and a section here. So for this section I have already written, for this section I am writing. So this section is like this. I write SF and BM. I have the P applied here, P, and this is X, and this is A, and this is RA. So the summation of M at point A is 0 will give me the BM plus SF into X plus A minus P into A is equal to 0. Yep, right. So that will mean BM is equal to P into A minus SF X plus A. Now SF we have already seen is equal to, for that section, that particular section, the SF is equal to P A upon L. Hence the BM will be equal to P into A minus P A upon L X plus A, right, which is nothing but PA 1 minus X plus A upon L, correct, right. So now at X equal to 0, BM is equal to PA into 1 minus A upon L, which is nothing but PA into L minus A upon L. Now L minus A is B, so PAB upon L. Now at X equal to B, which is the right hand end, BM is equal to 1 minus B plus A upon L, which is nothing but PA into 1 minus L upon L, which is nothing but 0. So the bending moment diagram for this beam looks like this. See, for the left hand section we have already seen that the bending moment was for left end is P into B upon L into X, where X is less than equal to, or rather I'll say 0 less than equal to X less than equal to A. So for this, BM at X equal to 0 was 0 and BM at X equal to A was PAB upon L. This number and this number are same. So the BM diagram looks like this. Goes up, comes down to 0. 0, 0. This is PAB upon L. This is a positive bending moment diagram. This is BMD. And for just for the sake of clarity and for the sake of revision, I just write a shear force diagram. This is like this. This is P, or rather I'll just say RB, and this is RA minus. So this is the SFD for simply supported beam.